sir.
Okay, so let's start with the problem and then we can move to our next topic. So obviously the first part of the problem is the same. You are given some load on some shaft or a axial bar, and you first find the stresses. Okay? In this problem, we are not going to, because we don't have much time left, so we will not go into that detail again. We have done that in the previous problem. Okay? So you directly go to the point where you have the bending stress, you have found the axial stress, and you have found the torsional stress. You have also found the fatigue stress concentration factors for bending, axial, and torsion. Okay? Remember, they would be different. Okay? For same geometry, but for bending load, for axial load, and for torsional load, you would have different fatigue stress concentration factors. Okay? And obviously material properties, and you would have the Marian factors to use the Marian factors to adjust the endurance limit, and this is the adjusted endurance limit. So now, in this problem, we start from the point that we have done all these things, and now we have found the bending stress, axial torsion, and their fatigue stress concentration factors, and we want to find the factor of safety for fatigue based on infinite life. Okay? So we start now because we have different. So if you look at the problem, the bending stress is completely reversed. Okay? So that means that you have the alternating component of bending stress, that is 60 megapascal, where the completely reversed means that the mean stress is mean stress for bending. Bending mean stress is 0. Now, for the case of axial stress, you have constant stress of 20 megapascal. That means that the axial stress has a mean component of 20 megapascal, but it does not have any alternating component. Whereas the torsional load is a repeated load varying from 0 to 50 megapascal. Okay? So that means that it is varying from 0 to 50. Okay? So that means the mean component, which is sigma max plus sigma min divided by 2, so that is 25 megapascal. And for repeated load, we know that the alternating component is also the same as the mean component, as you can see from this figure. So this is tau mean and this is tau alternating, and both would be equal to 25 megapascal. Okay? So now this is the case in which we have multiple bending stress, alternating and mean component, and axial mean and alternating component, and now we have to combine those. Okay? So we would use the distortion energy theory to combine these different stresses. Okay? So for alternating stress, we have the stress concentration factor for bending plus the stress concentration factor for axial, but we don't have any axial stress or alternating component for axial stress, so we can write it 0 here, okay, square, plus 3 into the fatigue stress concentration factor for shear stress multiplied by the alternating stress here, and similarly mean stress. So mean, we don't have the bending component, but we have the alternating component. And torsion component we have. So the first equation give us 1.4 into 60 square plus 3 into 5 square, whereas this equation would give us 1.1 into 20 square plus 3 2 into 25. So that would give you sigma A prime turns out to be about 120.6 megapascal, whereas sigma M prime turns out to be 89.35 megapascal. So only difference in combined loading is the way to combine these various bending, axial and torsion stresses into alternating and mean stress. Okay? That method is the method of distortion energy. After you have done that, the rest of the procedure remains the same as we discussed for previous fluctuating stresses method. Okay? So, so for example, if we use the modified Goodwin criteria, that would be 1 over a sigma prime SE plus sigma M prime SUT. Both values are, so this we have found at 20.6. So that gives us the fatigue stress concentration factor of 1.21. So modified Goodman theory predicts that this part will have infinite life, and as we know that the modified Goodman theory is probably on the more conservative side. So using other theories, this safety factor would be even larger. Now for yielding, we use again sigma A prime plus sigma M prime. Now previously this sigma A plus sigma M was basically directly equal to the maximum stress, but when you have different loading, so this is basically a little less than maximum stress. You can apply this individually by using the distortion energy theory to combine sigma A and sigma M. But we can use sigma A and sigma M directly, and we are a little bit on a conservative side. We would, in this course, we would follow this. So you have 320.6 plus 89.35. So that gives you fatigue stress concentration factor of 1.43. So the method is same as the previous method, the way we solve the cases of fluctuating stresses, but the only difference comes out to be in the way in which we combine the alternating and mean stress components, and that is the distortion energy theory. So first, if you are given a problem from obviously geometry and force, so you would find the bending stresses, axial stresses and torsion stresses, and obviously their repetition would depending upon the load repetition that would be obviously generally given to you. Load, bending load is completely reversed, or the shaft is rotating, for example, and axial load is constant, and torsional is a repeated load. Okay. And then you have to find the bending stress concentration factor, axial and torsional stress concentration factor. Okay. and in finding the inverse limit, we would use Ka as it is that we discussed previously. In Kb, we would use the formulas for change in diameter. So depending upon the size of the body, you would calculate Kb, and in Kc, you would use 1. Okay. And this Kc 0.85, that is for axial cases, can be covered here. Okay. That is alternating component. If the axial stress has an alternating component, then that can be divided by 0.85 to take care of the load factor. So, any questions?
No, sir.
So that takes us to the end of this fatigue failure theory. Now, our next topic is the most basic application, and actually most of it we have already covered in this chapter, and that is shafts, because most of our problems were related to shafts. So there is obviously nothing complicated about shaft design. It's just a simple application of fatigue failure theories. Okay? So we hope to be not spending too much time on this. So
सर हमें गुडमैन और लेंगर के अलावा कोई क्राइटेरिया यूज करने की जरूरत नहीं है ना?
गुडमैन और क्या?
लेंगर लाइन और गुडमैन, बस इसी से हम करें ना प्रॉब्लम्स अपने?
नहीं, बिल्कुल क्यों नहीं, जरूरत गड़बड़ भी करें। हमने लास्ट क्लास में गड़बड़ से भी अप्लाई किया था। और एक ही बात है, गड़बड़ एस्मी लेप्टेक, वो तो डिपेंड करता है आपको प्रॉब्लम में दिया हुआ क्या है। अगर आपको प्रॉब्लम में नहीं दिया हुआ कोई क्राइटेरिया, तो देन इट इज अप टू यू, जो मर्जी आप क्राइटेरिया अप्लाई करना चाहे। सोडरबर्ग अप्लाई ना करें, बस गुडमैन, एस्मी लेप्टेक और गर्बर में से जो मर्जी अप्लाई करें। बट अगर आपको दिया हुआ है कि गर्बर अप्लाई करें, तो फिर तो आपने गर्बर ही अप्लाई करना। तो लास्ट टाइम हमने जो प्रॉब्लम किया था उसमें हमने दोनों गुडमैन से भी सॉल्व किया था, सेफ्टी फैक्टर, और फिर गर्बर से भी सॉल्व किया था। ठीक है। सो जनरली ज़्यादातर हम गुडमैन ही यूज़ करते हैं और करते रहेंगे, क्योंकि एनालिटिकली गुडमैन, क्योंकि उसमें कुछ केयर वगैरह की टर्म नहीं, आसान है ज़्यादा। बट मतलब प्रोसीजर वाइज कोई डिफरेंस तो नहीं है उसमें, दोनों एक ही जैसे। ओके, सो let's start with this topic. So shafts. So shafts, obviously the ubiquitous device in mechanical engineering. All machines generally have a shaft. So what is its purpose? It transmits. We all know it transmits rotary motion and torque, generally from some driving devices that are maybe engines or motors, and from one location to another. Okay. And usually they are have a circular cross section. Okay. And they carry gears. Okay. Shaft carry gears on them, or they have sheaves or struck. Okay. So gears, we know cars, gear trains, all have gears in them. ठीक है. Sheaves or pulleys. ठीक है. So these are used in lathe machine and etc. ठीक है. The difference is when you have to transmit power, but the locations are close together, you can use gear. But when there is a significant difference between the points where you want to transmit power, ठीक है, then obviously we can either use pulleys or sprockets. ठीक है, so both can easily transfer power to a much larger distance. But in these, the difference is obviously the sprockets have positive drive, whereas the sheaves have some slippage in them. Okay. So cost wise, this would be cheaper compared to this. Okay. But this will have positive drive and this will have some slippage in it. Okay. So we from lathe machines and etc. you can see that the power is transmitted through sheaves and pulleys, whereas sprockets are used in camshafts of higher end automobiles, or you have all seen them in bicycles. Okay. So sprockets and chains are used. Both of these have positive drive, whereas this has some slippage. Okay. So cost wise, obviously these two are higher and this would be on the cheaper side. Okay. Before moving further, let me just clarify one thing, that we are not obviously discussing axle. And what is the difference between axle and a shaft? Can anybody tell me what's the difference between axle and a shaft? हाँ भाई, कोई है जिहाद?
सर कंफर्म नहीं पता
चले, जो पता वो बता दे।
सर। एक्सेल सेंटर शाफ्ट होती है और सेंटर के लिए सिर्फ यूज होती है।
सेंटर के लिए? सेंटर क्या है?
जैसे साइकिल है तो उसकी सेंटर जो शाफ्ट होगी वो एक्सेल होगी।
अच्छा, चले, और कोई? एनीबॉडी एल्स?
सर शाफ्ट पावर को ट्रांसमिट करेगी और एक्सेल जो सिर्फ स्टेशन स्टैटिक होता है।
एक्सेल स्टैटिक होता है, ठीक है। एनीबॉडी एल्स? ओके, सो जी उस्मान।
सर एक्सेल लोड को भी बेयर कर रहा होता है।
अच्छा, नहीं लोड, ठीक है, चले। सो लोड ऑब्वियसली बेंडिंग लोड तो कोई भी शाफ्ट है या एक्सेल है, both would have some bending load. If even not for anything, then it would be for the weight of the axle or the shaft. ठीक है. True axle, जैसे शहीद ने कहा, ठीक है. So true axle is an axle which does not rotate, and so anything attached to that is rotating. So for example, in horse carriages, you can see a axle on which some wheels are rotating, but the axle itself is not rotating. ठीक? So it is only subjected to bending moment. But even an axle, nowadays we call axle which are rotating as well. So for example, the in railway axle. ठीक है? So railway axle is rotating axle. Okay. So if you like to define axle, you would say that it can be rotating or non-rotating. Okay. That is not the distinction. The distinction is that it must not transmit power. Okay. So there could be bending loads in it, and obviously when it would, if it is rotating, so it would have a completely reverse bending load, but there is no torque being applied or power being transmitted through it. Okay. So, for example, a railway axle is used to connect the wheels, railway wheels, but the power is not directed to that axle. Okay. So, whenever you have the same geometry, but the power is also there. Okay. The power is also there, or torque transmission is there, then you can say that it is a shaft. Okay. So, in terms of stresses, if we say if the axles are only subjected to bending moments, but there is no twisting moment, or torque involved. Okay. So if the torque is involved, then we can call that a shaft. Okay. So shaft must be transmitting some torque from one location to another. Okay. So now in the obviously shaft design, so we can design from the strength perspective, or deflection is also something we have to take care, or there also the whirling of shaft, so we have also have to take care of the vibration. Okay. So in this course obviously we are more focused toward the strength part, okay, but deflection we have calculated in mechanics of materials, and similarly you can calculate in this also. Shafts also same, they act like same as the beams, and in your textbook you also see various deflection limits. So we would maybe later talk about the deflection limits. Okay. So similarly as the strength limits, okay, so you have the yield strength and such that. Similarly we have deflection limits for various attachments on the shaft, and we will discuss them later. And in terms of materials, so to obviously deflection is a problem in shaft. So generally we use material with high modulus of elasticity, and that is steel. The grades, the high strength grades do not matter, because usually we know that all steels have approximately same modulus of elasticity. Okay. So in terms of strength, because generally shaft are not too much stressed part, okay, so we generally can use low to medium carbon steels. Okay. Now in applications where corrosion is a factor, okay, so for example in marine application, so then you can use the, for example, bronze, or move towards alloy steels. So now later on we would see shaft design, and you would see that the design procedure is just a simple application of the fatigue failure theories, the modified Goodman, or the failure theory that we have already discussed. Okay. But in designing the shaft, the one thing that maybe students don't care for too much, or don't put too much attention into it, is the shaft layout. So designing with in terms of stresses is easy, and you have done that previously. Okay. But what is the shaft layout, and how to select that? Okay. So that is a, you would say, a relative new concept, especially when you're faced with final year projects. So every project generally have some, obviously mechanical projects have some shafts in them. Okay. So whenever the time comes to designing of those shafts, ठीक है, the layout poses more challenge than basically calculating the stresses and so on. ठीक है. So let us discuss a shaft layout problem. ठीक है. So So the problem is that we want to transmit power from this shaft to this shaft by going through gear reduction. ठीक है. Now, so obviously gear reduction means that you are using a larger gear to connect to this shaft and smaller gear to connect with this shaft. Now I have drawn these shafts, so we won't be considering at the moment these two shafts. We are basically interested in this third shaft that is used to transmit the power from this shaft to this shaft. Okay? So if this is one and there would be some shaft here, so this is 2 and this is 3. Okay? So we are primarily interested in this shaft. Okay? So and at the moment we are discussing the layout of this shaft. So what should be the length of the shaft, where the gears must be positioned. Okay? So the first question that we are faced is the location of gears on the shaft. Okay? So obviously as a designer, nobody is going to tell you that okay, this distance should be 200 millimeter. Okay? We don't know. Okay? This is up to you. What should be this distance? And obviously I've drawn these shafts as unknown, so whatever this distance you choose, you can basically move this in this direction and close to each other or away from each other. Okay. So let us only think about this shaft. Okay. So you have on this shaft you have two gears. Okay. One is a large gear where the input power comes from. One is the smaller gear where the output power goes to. So what is the how to decide about location of the gears on the shaft? So that is the first problem of the layout. Okay. So at the moment there's no concrete reason to choose any distance. So these could be close together or these two could be far apart. Okay. So can you think of any reason? What should be their distance? Should they be close together? Should they be far apart or whatever? What should be their distance?
सिमेट्रिकल अगर हो, अगर सिर्फ वो सिमेट्रिकली लोकेटेड हो.
Symmetrically किसके हिसाब से? What do you mean by symmetric?
जैसे सर अगर एक शाफ्ट के 20 सेंटीमीटर पे एक है तो दूसरा भी दूसरे साइड के 20 सेंटीमीटर पर हो.
अच्छा. So with respect to shaft length, they would be मतलब आप कह रहे हैं कि अगर ये कोई सेंटर लाइन है तो उस सेंटर लाइन के वो सिमेट्रिकली डिस्ट्रीब्यूटेड हो, ये कहना चाह रहे?
जी जी सर।
ठीक है, क्यों, उससे क्या फायदा होगा?
फायदा सर, बस देखें इस तरह की चीजें थोड़ी सी, इसलिए कह रहा
चले,
था।
सो मैं यही बात कर रहा हूँ कि डिजाइन में अगेन ऑब्वियसली कोई ऐसा डायरेक्ट आंसर तो नहीं हमें मिलने लगा, ठीक है, बट वी वुड हैव सम जेनेरिक रूल्स, ठीक है, बट ये जो आपने बात की ना, ये अगेन दैट इज प्रेडिकेटेड अपॉन द लेंथ ऑफ द शाफ्ट, ठीक है, एंड लेंथ ऑफ द शाफ्ट इज आल्सो प्रेरोगेटिव ऑफ द डिजाइनर, सो यू हैव टू चूज द लेंथ ऑफ द शाफ्ट, ठीक है, सो so we can, at the moment I don't think there is any reason to decide upon what is what should be the distance between the gears, okay, so we would, I think, move on and just keep it in our mind that this is a problem that we need to discuss, but we move further, so maybe when we move further we would find some hints to where these gears should be located. So another problem would be the location of bearings. Again, location of bearing depend upon the length of the shaft, okay, and what are the considerations? So that means so what are the consideration for length, okay? So there are two consideration, I think, for length, we can say, is that longer the shaft, okay, you can easily understand. So if for example I placed bearings here in the simply supported configuration, okay, so the longer the shaft, the higher the moments in this central region, okay? So you have some reaction force here and reaction force here, and those are creating moments, okay? So the longer the shaft, the moments become larger, but so in that sense, so if we look from the stress point of view, the shaft should be as smaller as possible. But the other consideration obviously is assembly and disassembly. Okay. So if you make a shaft very small, okay, the problem would occur in assembling and disassembling this component. So if you have worked with any machine, you know that you need some space. So if you have to attach gears and things like that, or sprockets or sheets, then you need some space to work with. Okay? So in assembling and disassembling, you need some space. Okay? So so, so generally the rule is for length, okay, it should be as small as possible considering the assembly and the housing constraints. So wherever you, obviously it depends upon the external housing as well in which the shaft is located. So not everywhere you can locate the bearings, okay, but depending upon these two constraints, the shaft should be from the moment point of view as small as possible, okay, but generally we need some distance for easy assembly and disassembly, okay. So this is the first consideration in terms of choosing for length. Now another problem with choosing the location of bearing is whether to have this layer shaft in simply supported configuration or the overhanging configuration. Okay. So in simply supported configuration, you have all the attachments inside the bearing and not much of the shaft outside. But when you go for the overhanging configuration, okay, you have some shaft attachments outside the bearing as well. So another problem that you need to decide while deciding the layout is whether to have the shaft in simply supported configuration or the overhanging configuration. Okay. So generally from the stresses point of view, the simply supported configuration is preferred, okay, unless we have some attachments that require overhanging portion. Okay. So what could be the attachment that could require the overhanging portion? That should require the shaft, the bearing should be inside, and there must be a part of the shaft outside to that overhanging part. So what kind of attachment could require that? Any prediction? No. I think if you think about it, see, obviously bearings are connected to the housing. Okay. So if you have sprockets and chains or sheaves and pulleys, okay, so you can especially for pulleys we need this overhanging portion, okay, because if the pulley is located inside, okay, and obviously we have belt running over it, and belts are something that require frequent changing, okay. So you would have to disassemble the whole these bearings and the housing to remove this belt if it is inside the bearing, okay. But if the pulley is outside the bearing, okay, the removal of the belt becomes much easier, okay. So when you have pulleys, generally we use this overhanging portion. But apart from that, if we are designing the shaft for gears, okay, you would only be generally we prefer simply supported, because from the moment point of view, less moment involved. Okay, and even if you have this overhanging portion, or this basically becomes a part of cantilever beam, we will try to make this part as small as possible. Now, another problem is in choosing for bearings is uh, whether to use two or more bearings. Okay. So what are the advantages and what are the disadvantages of using more than two bearings? Okay. Now we would generally we use only two bearings. Okay. So if we are in the simply supported configuration, we use only two bearings at the end. But if the length of the shaft is much larger, and so that would mean that the deflections basically would become much higher in this central region. So if the length due to assembly or disassembly, if there are multiple components that are attached to this shaft, so then we can think about adding another bearing. But the problem with addition of these bearings would be, if you put a little thought into it, you can easily understand that with two bearings, the alignment of the shaft is much easier. Okay? But if you install a third bearing, then alignment becomes a problem. Okay? And now the machining has to be very much perfect for these three bearings to align into a single line so that shaft can pass through that. Okay? If you have only two bearings, small amount of difference in alignment can be taken care of. ठीक है. But if you have 3 bearings or even more bearings, then they need to be perfectly aligned for the shaft to be able to rotate in these bearings. Now, so for example, in our problem that we started with, we had to reduce gear reduction shaft basically. So, so we choose a simply supported configuration. Okay. Now, so we have these bearings at the end, and they are connected obviously to the housing. Okay. Now, to now the next major problem is that at the moment the configuration that the shaft is, this shaft can easily move like this. Okay. So you can have an axial movement while rotation, and obviously that is not desirable. Okay. So we need something to locate the shaft axially. Okay. So how to locate this shaft? How to stop this axial movement? हाँ भाई.
बेरिंग से है.
बेरिंग एक्सियली लोकेशन को कैसे रोकेंगे? वो तो बेरिंग में तो रोटेट करेगी ना शाफ्ट.
थ्रस्ट बेरिंग होते हैं ना
जी.
सर, थ्रस्ट बेरिंग जो होते हैं.
अच्छा, आप कह रहे हैं थ्रस्ट बेरिंग यूज करें. अच्छा, चलें, ठीक है, थ्रस्ट बेरिंग यूज कर सकते हैं. और
सर कॉलर्स यूज करने.
अच्छा, ठीक है. सो वी कैन यूज क्लैम्प कॉलर्स की बात कर रहे हैं. ठीक है. और क्लैम्प कॉलर आप बेरिंग के साथ कैसे यूज करेंगे? क्लैम्प कॉलर तो आपको रोटेशन भी देगा ना साथ साथ. चले, बहरहाल, एनीथिंग एल्स? Okay, so the most obvious choice is shoulders. ठीक है. You would provide shoulder. ठीक है. And a shoulder here as well. ठीक है. Thrust bearing, yeah, generally जो thrust bearings है ना, they are catered for if you have a significant you need them if you have a significant axial load. ठीक है. So we are at the moment not talking about that there are significant axial loads involved. ठीक. But still, whatever you install, it should be axially located. ठीक है. So the most simplest solution is obviously to use shoulders. ठीक है. So we can use shoulders, or we can use retaining rings. Okay. So at this end we can attach a retaining ring, and I am purposefully, just for clarity, leaving this gap. Okay. In reality, obviously, the shoulders and the bearings would be connected together. Okay. And you can use a retaining ring on one side. Okay. And obviously, if the axial loads are very low, we can use press fit. Okay. So retaining rings, shoulders, obviously axially locate the shaft, but they also cause stress concentration. Okay. Press fit do cause a small bit of stress concentration, but the amount is much less than the shoulder and rings. But obviously, they cannot be used for large axial loads. And also for press fit, you obviously need higher tolerances. Okay? So the machining cost would be higher. So now, so we have decided the length of the shaft based on the assembly disassembly considerations, and then to locate the shaft axially, you would need some shoulders. Okay. So now the next problem would be how to attach the gears. Okay. So as we discussed previously, the easiest solution would be to use shoulders for them as well. Okay. So we have these bearings at the end, okay, that are connected to the housing. Okay. And now you have to attach the gears. Okay. Again, the location of the gear should be close to the shoulders. Okay. And what about the location of the gear with respect to okay, the first problem is again the axial location. Okay. In terms of axial location, okay, how to locate these gears axially to stop their axial movement. Okay. So we can use shoulders on one side, okay, and on the other side we can use, for example, retaining rings. Okay. So you can use shoulders and retaining rings. Another consideration would be what should be the location of gear with respect to bearing. Okay. So generally for moment considerations, okay, because the moment obviously if you are in simply supported configuration, then the moments are 0 at the bearings. Okay. So the gear attachments should be as close as possible to the bearing, keeping in mind the assembly disassembly constraint. Rather than being in the center of the shaft, okay, they should be away from the center and close to the bearing. Okay. So what Sharis said at the start, they are generally away from the center and equal distance away from the center. The reason is that we want to lower the moments that are involved in shafts. So for that we want to install the gears or sheaves, sprockets as close as possible to the bearings. Okay. So now a shaft that we have mostly seen as constant round cross section. Now we see that generally the shafts are not like that because you have to attach various gears and bearings to that shaft, and for that you need some kind of shoulders and things like that. Now, in attachment of the bearing, the only consideration was axial location. Okay? But when you attach the gear, okay, there is apart from the axial location, there is another consideration of torque transformation. Okay. So how do we transfer the torque from the gears to the shaft and for input gear? Okay. So how do you connect this so that the torque is transferred from the gear to the shaft and there is no slipping involved? ठीक है, उसके लिए क्या करें? हाँ भाई, एनी आइडिया? टॉर्क ट्रांसफर के लिए क्या करें? खैर कुछ तो पढ़ा होगा आपने, शीट डिजाइन 1 में इससे रिलेटेड कोई चीज आपने देखी है जो टॉर्क ट्रांसफर के लिए यूज होती है?
सर बेल्ट्स होते हैं, गियर्स होते हैं।
नहीं, बेल्ट्स और गियर्स तो एक लोकेशन से दूसरी लोकेशन है ना। अब आपने गियर शाफ्ट पे अटैच करना है तो शाफ्ट, वो गियर तो स्लिप करता रहेगा शाफ्ट के ऊपर, वो शाफ्ट कैसे इंश्योर करेंगे कि शाफ्ट और गियर इकट्ठे रोटेट करें?
की यूज करेंगे।
कीज।
बिल्कुल बिल्कुल, सो वी कैन यूज कीज, ठीक है, और वी कैन यूज पिन्स, ठीक है, पिन भी यूज कर सकते हैं। सो वी कैन आइदर हैव सम की इन्वॉल्व, ठीक है, सो जिस तरह वुडरफ की है, पैरेलल की है, जिबेट की है, ठीक, और यू कैन हैव पिन्स, ठीक है, फ्रॉम सो फॉर एग्जांपल so you can design your gears to be such as that there is a hub, gear hub is attached like this, and then we can have a key passing through here, ठीक, so passing through this hub part from this to this, ठीक, so you can use a pin passing from this hub part to this hub, ठीक, so we can use pin or we can use splines as well, ठीक, splines obviously are gear like teeth on the surface of the shaft, okay, so we can create a gear like teeth on the surface of the shaft and on the inside of the gear, and they can mesh together so for torque transfer, okay, so all of these methods we can use, okay, so these are some of the methods that we can use for torque transfer. Now, the main purpose of this discussion was to make you aware of the problems that occur. One, so if we summarize this, okay, so the problems that occur during the axial layout of components, okay, so you have to axially locate every component on the shaft, okay, so they the points should not move, okay, so wherever you have gear attached or wherever you have a pulley attached, you must make sure that there is some provision that stops that gear from moving, okay, and then you also have to support some axial loads, okay, So for example, if you are using helical gears or bevel gears, they always have an axial component in them. Okay? And then you also have to provide for torque transmission. Okay? So to make sure that gear transfer the torque to the shaft. Okay? And also at the end we have the also have to take care of the assembly or disassembly constraints. Okay. So these all issues we have to take care of in deciding the axial location, how to locate or where to have these gears and these devices. Okay. And we have seen that all these additions generally cause some kind of stress concentration. Okay. So the real shafts generally look like this. They have these kinds of stepped shoulders for these attachments, okay, that are added to them. Okay. And this so this is the schematic diagram of a retaining ring. Okay. So generally, if you have a bearing, so on one side we can use a retaining ring. So you can have a groove on the shaft and a retaining ring attached to that to stop this movement of the shaft. Okay. But remember that again this causes a lot of stress concentration. Okay. And for torque transfer, you can have a key attachment with the hub of the gear. Okay. But in keys generally the keys only allow for torque transmission. They do not axially locate. Okay. So you have to use the keyway in combination with retaining ring or set screws, things like that. Okay. But some keys, for example, jib head key, you can use, so that also actually locates the shaft as well. But generally, most of the keys only provide for torque transfer. And then we have the splines. Okay. So spline is the inside of the shaft. You can make that gear teeth on the outside surface of the shaft and the inside of the gears, but they are only used when you have very high torque transfer and there is chances of slippage. And one thing that you must remember, so our case in which one thing that you must remember is when you are attaching a motor. So in our example that we discussed, there was no motor involved. Okay. But if you ultimately, obviously, whenever machine you are designing, you would have some power device. So it could be an engine or it could be motor. So generally, in most kind of the shaft that you would be designing for your FIP, you would be using a motor. Okay. So you have to remember that you okay, never use a motor for never use it for location of the shaft. ठीक है. ठीक. So आपने मोटर obviously housing के साथ attached है. ठीक है. So this is motor. ठीक है. And this is attached to the housing. ठीक. So you don't use it you don't directly connect this motor to this housing to this shaft, so that this motor drives the shaft as well as locates the shaft. ठीक है, ऐसा नहीं करना. ठीक है, you have to first locate the shaft. ठीक है, तो आपने ये शाफ्ट है, इसको आपने शोल्डर्स के थ्रू फॉर एग्जांपल लोकेट कर लिया. ठीक है, नाउ इट कैन नॉट मूव लाइक दिस. ठीक, एंड दिस सिस्टम should be completely independent from your power transmission system, power transmission device. ठीक है, so that it can, for example, if you try to manually move this shaft and there are associated shafts, so they all should move even if you give it manual power. ठीक, and then you can attach this motor to this shaft through a coupling. ठीक है, it could be a rigid coupling or rolled arm coupling or whatever, depending upon direction of your device. ठीक है, but remember that never use the motor for location. ठीक है, attach this motor through some kind of coupling to the shaft. So now in this figure you can see these things more clearly. So here, so this is one example of a shaft layout. So first you can see a shoulder here, and that shoulder is for this bearing and this bearing. You have a gear here, a sprocket here, and a sheave here. Sheave, you can see that it has been attached on the outside. Okay? On the overhanging portion. Why? Because of easier assembly and disassembly of the belts involved. And you can see that there is some small difference here, whereas this bearing is attached to the shoulder. Okay? This difference is generally kept on one bearing for to allow for some thermal expansion. Okay? Now, for attaching these sheaves, gears, can you hear me?
No, sir.
जी सर, अब आ रही है आवाज
अब
सर,
सुन।
स्लाइड शेयर नहीं है.
अच्छा, ये कहाँ से स्टॉप हुई है?
वैसे
सर,
एक
एक
मिनट
मिनट हुआ
नहीं
है।
हुआ अभी.
हैं? यही
एक
फिगर
मिनट
डिस्कस
सर
कर रहे
बस हुआ है अभी. जी जी
मैंने
सर,
कहा
यही थी.
यही फिगर. अच्छा, सो इस फिगर में जो हम डिस्कस करते रहे हैं लेआउट के जो मसाइल, ठीक है, सारी चीज़ें इस फिगर में वी कैन सी देम कंबाइंड. ठीक है, सो फर्स्ट ऑब्वियसली यू हैव टू लोकेट द बेयरिंग्स. ठीक है, बेयरिंग लोकेशन के लिए स्टेप्स दिए हुए, and you can see on this side there is small gap, some small gap. ठीक है, this axial clearance is generally given on one bearing for thermal, to allow for the thermal expansion. ठीक, then the sprocket, gears, pulley is on the overhanging side. Why? Because of easier assembly disassembly of the belts. ठीक, and all of these on one side, sprocket, gears, and sheave have a shoulder on them, shoulder on the shaft for axial location, and you also have so snap ring is attached to the bearing on this side to completely stop this movement. Okay. And then for providing for torque transfer, you can see that we have this key, Woodruff key, you can see installed with this gear and the gear hub and the shaft. Okay. Here you can see a clamp collar. Okay. And here you can see tapered pin. Okay. So these are some of the common methods to transfer torque. Okay. But uh, each has its own you can say advantages and disadvantages. So for example, if we talk about keys, okay, now advantage is obviously it is easy to install, disassembly installation, yeah, or you can say assembly disassembly is very easy. Okay. But and also you have accurate phasing. Okay. There is no chance of slipping involved, and you can also have the accurate phasing. That means that there is no chance of slippage that is involved. But the disadvantages are that there is generally for most of the keys there is low or very little resistance to axial movement. Okay? So you cannot use key for axial location. Okay? While for example pin not only provides for torque transfer, it also axially locates the component. Okay? Another advantage for key would be that we can design the key to be the first part to fail, so to be on the weaker side. Okay. And also another problem is the clearance. Okay. So for assembly disassembly you need a small clearance, but if you have load reversals, okay, so that clearance can obviously cause a backlash. Okay. So compared to, for example, if you talk about pins, okay. Now pins again have very accurate phasing. Okay. So there is no chance of slippage involved. Okay. And obviously they can also be failed fast. Okay. And can locate axially as well. Okay. But the problem is high amount of stress concentration. You have to have a hole in the shaft. Okay. So it has high stress concentration factor. And obviously we can in terms of stress concentrations we can see that for example the clamp collar here is so you don't need to have any discontinuity in the shaft or in the even in the hub to attach a clamp collar. So from the stress point of view, this clamp collar is better, but again the problem would be for clamp collars. The problem could be no phasing. Okay. You have a chance of slippage when you are attaching, because clamp collars obviously are working through the effects of friction. Okay. So you cannot accurately phase these two shaft and the gear, or shaft and sprocket. There would be some slippage that would be involved. Okay. The same is the case with press fits. Okay. You both have very small stress concentration factors. Okay. They still cause some kind of stress concentration because press fits obviously can cause fretting corrosion and things like that. Okay. But the both have imply that there is no phasing involved. Okay? So once again, it's you have to compromise on whether you want phasing, accurate phasing, or so that comes with a higher stress concentration factors, or you can compromise on the phasing and reduce the stress concentration factors. Okay. So any questions from this? Layout, location?
सर ये
No, sir.
पेन्स
जी
का
राफे
बताया था सर, थोड़ा ये अपना बोर्ड लेफ्ट साइड पे क्या
बोर्ड लेफ्ट साइड पे जी
तो ये एक्यूरेट ये क्या लिखा है आगे,
फेजिंग
इसका क्या मतलब?
एक्यूरेट फेजिंग का मतलब है कि दे वुड रोटेट साइमल्टेनियसली. फेज शिफ्ट नहीं है, ठीक है. फेज शिफ्ट बेसिकली दिस टर्म आपने मैथमेटिक्स में
ठीक
इस
है
तरह की
सर,
चीज, ठीक है. तो अगर आप चाहते हैं कि गियर और जो शाफ्ट है बिल्कुल इकट्ठे रोटेट करें, उनमें कोई गैप नहीं होना चाहिए, ठीक है, तो तब ऑब्वियसली कीज एंड पिन्स आर प्रेफर्ड, ठीक है. बट अगर आप क्लैम्प कॉलर्स या प्रेस फिट यूज करेंगे तो फिर यू कैन नॉट क्लेम दैट दे हैव एक्यूरेट फेजिंग, ठीक है. देयर वुड बी सम स्लिपेज इन्वॉल्व, हाउएवर minuscule, but there would be some slippage involved, ठीक है. But their advantage is that they do not cause much stress concentration, ठीक है. So it depends upon the amount of torque, ठीक है. So if you have a high torque, you would choose these or this, ठीक है. This obviously combines axial location as well, ठीक है. But if you have very low torque, then you can go for these. और बहुत ही ज़्यादा टॉर्क है, देन ऑब्वियसली वी कैन गो फॉर स्प्लाइंस, बट स्प्लाइंस आर जनरली ऑब्वियसली एक तो स्ट्रेस कंसंट्रेशन भी बहुत ज़्यादा है और साथ में दे आल्सो आर एक्सपेंसिव टू मेक. एनी अदर क्वेश्चन? ठीक है. सो ये लेआउट को जनरली स्टूडेंट्स क्या कहते हैं, इतना सीरियस नहीं लेते, ठीक है. बट ये लेआउट जब आप एक्चुअल में डिज़ाइन करेंगे तो स्ट्रेस कैलकुलेट करना इज नॉट अ प्रॉब्लम, ठीक है. अभी हम देख लेते हैं स्ट्रेस का फार्मूला कैलकुलेशन के लिए, वो बहुत आसान काम है कंपेयर टू दिस पार्ट, ठीक है. दिस इज द मोस्ट डिफिकल्ट पार्ट बिकॉज यहाँ पे आपको कोई फार्मूला नहीं अवेलेबल कि यार अच्छा अब हमने कितनी लेंथ रखनी है, ठीक है, और किधर गियर अटैच करने, ठीक है. सो यू हैव टू हैव at least know the general guidelines of where to attach the bearings, where to attach the shaft, what does location mean. So most of the students, even when they are designing their FIP or doing that, they even don't know what does location mean, ठीक है. So वो उस वक्त जब वो एक्चुअल प्रॉब्लम में आते हैं तो तब आप समझ आती है कि यार लोकेशन है क्या. तो लोकेशन का पता होना चाहिए, लोकेशन के लिए क्या चीज़ें, क्या गाइडलाइंस है, ठीक है. Then obviously it is up to designer and you can go through iteration and stuff like that. So next we can move to shaft design, ठीक है. So we have discussed shaft problems previously in the fatigue failure theories. Every shaft we know that even if there is no other loads, there is a weight of the shaft, and the weight of the shaft because the shaft is rotating is causing fatigue, ठीक है. The bending moments are changing at each point, so shaft is always a fatigue problem. And generally you have transverse load transmitted through gears, ठीक है, or the sprockets, ठीक है. They are all causing transverse load, so they would be playing their part in causing fatigue. And you also have combined that with some torque. So shaft, we know that by definition they must be transmitting some torque. So there is also an addition of torque. So torsional loading is there and the bending loading is always there. Okay. It can be combined with axial loading in some cases, or it there can there is no there would be cases where there are no axial loading, but generally bending moment and torque would always be present. Okay. And we saw that the first task is so obviously the stresses are different throughout the shaft, okay? But we don't need to evaluate the stress at all points. Okay? We only need to evaluate the stress at critical locations. Okay? Now that obviously takes some judgment, that you have to judge what are the critical locations on that shaft, because as I said that the most probable loading is bending moment and a torsional moment. Okay? And both bending moment and torsional moment are maximum at the outer surface. Okay? So you have large bending moment and torsional moment. Okay? So generally we don't calculate these stresses at inside the shaft, but only at the outer surface. And on the outer surface, so obviously throughout the length of the shaft, on the outer surface, even on the outer surface, the stress is changing. So we evaluate the shaft at points where stress concentration exists. Okay. And bending moment generally are maximum towards the center and zero at the bearings if you have a simply supported configuration. Okay. But obviously we also in evaluating what is the critical location, you also need a shearing force and bending moment diagram. Okay. So combining this information with stress concentration and only catering for the outer surface, we can identify the critical location. Okay. So axial loads generally, if they are due to helical gears or the bevel gears, they can be neglected in stress calculation, not in terms of axial location. Axial location में आपको उसका ख्याल रखना है. But in terms of stress calculation, because we know that the axial stresses are generally much less than the bending moment, so we can generally neglect them and focus on the bending and torsional stresses. Okay. So we have so generic formula we all know for calculating of bending moments and torsional moments, but we can for shaft problems we can generally customize these formula. Okay. So one method is to directly use these formulas and the method of chapter 6, and it is still valid, or we can customize these formulas, for example by putting in this. So generally if shaft design कर रहे हैं, क्योंकि अगर आप design कर रहे हैं, you would be needing the diameter of the shaft, so we can, so for example we can convert this I in terms of D and C in terms of D. So sigma A comes out to be this. And similarly the alternating component, so J की जगह obviously जब D put करेंगे तो pi D4 over 32. ठीक है, वो pi R4 by 2 था तो pi D4 by 32. Okay. So that gives you 16 Tm pi D cube. ठीक है. And same is for the mean bending stress, so that depends upon the mean moment, and the mean torque. Torsional stress depend upon the mean torsion. Okay. So once you have that, you can combine that using distortion energy theory. Okay? So that would be and we can write a similar equation for the mean stress. Okay? I'm not writing it again. Okay? And then for example, we can use the modified Goodman equation to combine to take into effect the combined effect of alternating and mean stresses. Okay. So generally, it's more easier to write this equation in this form. Okay. And for sigma A and sigma M, we can replace this term, and we can also so by putting in the value of sigma A and sigma M, you get this equation. Okay? And obviously, after some simplification, that is, you take 16 pi d cube outside, and we can easily now convert this equation in terms of d. Okay? Convert this equation in terms of d, you get this. Okay? So this equation obviously is for design. Okay? So when you are designing, then you would be interested in calculating the diameter given the loads, and this equation is generally used for analysis when you have the loads and the diameter and you are calculating the safety factors. Okay? There is nothing new about it. We have just customized this equation by for replacing for bending stress and the mean stress that occur in circular shafts. ठीक है. So shaft का जो bending stress का formula है my over I और PR over J में उसमें I और J में shaft के जो हमने pi R4 और pi R4 by 4 और pi R4 by 2 enter किए in terms of D. With simplification we get this formula. ठीक है. We can so this combination is basically called the distortion energy Goodman fatigue failure criterion for shaft. Okay? And we can do the same with Gerber. You get these two equations for analysis, this one, and for diameter, this one, and also for, so that is called the distortion energy and Gerber equation, and this is the distortion energy and SP elliptic equation. Okay? So either you can use these equations directly or you can still follow the methods of the previous chapter. Okay? Both would give you the same result. Okay? And obviously these equations are given in your textbook. Okay? So these are D Goodman, D Gerber, and D SP elliptic. Okay? And generally, lastly, for yield check, obviously we need the Langer criterion. So we apply this coin. Okay? And this is obviously on the conservative side. Okay? And lastly, because in when the shaft is rotating, So the bending moment at the critical location is generally in terms of it is changing in a fluctuating pattern. Okay. So you would see most of the shaft problems, the bending moment is something like this. So that would mean that there is some alternating component to the bending moment, but the mean component is 0. Okay. Whereas the torque is generally steady. So the direction of shaft usually is rotating in one direction. So torque is steady. Steady torque means that there is some mean component of torque, but the alternating component is 0. So this is the most usual case for shaft design. So we can put these tau alternating into 0 and mean moment into 0 in the equation, combined with these values to get the values for the safety factor and for diameter. So next time we would talk about the how to estimate, because for for stress concentration calculation we also need to know the diameters. ठीक है, but अगर आप डिजाइन कर रहे हैं तो obviously we don't know the diameters first hand. So next time, let's start with this discussion of estimating stress concentration factors, and then we can move to a problem related to